yeah, so basically I'll try to explain the title throughout the talk. So I'm going to start with a brief explanation of what is Floer homology. It's not going to be a very sort of historically enlightening explanation. For that, you should have went to Helmut's talk that was some weeks ago. But I'll try to describe that. So in one sentence, basically, you can think of Floer homology as a construction that relates some certain flows on a manifold with the topology of the manifold. Or in a longer sentence, it's a chain complex that is generated by periodic orbits of these flows and whose homology is a topological invariant of the manifold. This construction can be seen as an infinite dimensional version of the simpler homology theory called Morse homology. So I'm going to start with saying what is that. Then I'll sort of recall what we're dealing with in symplectic geometry and explain how to see Floer homology as an infinite dimensional version of this Morse homology. So all of this part is very classical, goes back to the 80s. And then the more modern part is looking at this construction specifically for flows that are supported on a subset of the manifold. So you have a closed manifold, you have a subset, and your flow is basically constant outside of this subset. And then you want to know what you can say about this construction. Can you, in some sense, localize the construction? Can you study some quantitative measurements specifically for such Hamiltonians? And basically things behave significantly differently if depending on whether the second homotopy group of M vanishes or not. So I hope that it will soon be clear why such a maybe odd condition matters. But generally, if the second homotopy group vanishes, then things tend to be simpler and sort of more similar to the finite dimensional case, to Morse homology. And if not, then there's less you can say, basically. Okay, so let's start with, oh, and I should say, like, I guess there was like a mixed audience, so please ask me anything or tell me to rush or slow, whatever. Okay, so starting with Morse homology. So our setting is basically, we have a Riemannian manifold that I'm going to assume is closed. And we have, so for example, think of the two-sphere, and we have a function from this manifold to R, which is a smooth function. And we're going to assume that it's non-degenerate. This non-degeneracy condition is called Morse. It's a Morse function. Basically means that the Hessian is non-degenerate on the critical points of this function. And in particular, it has finitely many critical points. So for example, think of this height function on the two-sphere. So this is the two-sphere. Basically, F sends this circle to this point, and so on. Okay, so a natural question is, how many critical points must such a function have? In other words, we want a lower bound for the number of critical points of F in terms of the manifold N. So in order to answer this question, one can follow the following plan. So you can construct a chain complex that is generated as a vector space by the critical points of F, and show that this is one, and then show that the homology is a topological invariant. And then the lower bound would be the dimension of this homology, sorry. Okay. So this is basically what's done by Morse homology. So the Morse chain complex at level K is generated as a vector space, let's say over Z2, by the critical points of F of index K. So here, this K is the Morse index of the critical point, namely the number of directions going down. So for example, on this picture, the function has 4 critical points. This one is the maximum of index 2. It has 2 directions going down, the saddle of index 1, and the 2 minima of index 0. Now to make it into a chain complex, we need to define a differential. So the differential of a critical point X will be defined by summing over all critical points of index 1 lower. So here this is going to be y, and the coefficient will be the count mod 2 if we're working with Z2 coefficients of the number. So this the count of the flow lines of minus gradient f from x to y. So let's work this on our example. So the let's give names to these critical points. So this is going to be x, y, z, and w. And so the differential of x is, well, the only candidates to participate in the sum is y, and then how many flow lines we have going from x to y. We have one on the front and one of the back on the back, and we count mod 2. So this is going to be 0. The differential of y, well, the candidates are z and w, both of them of index 1 lower, and the coefficients are going to be just 1 because we have one negative gradient flow line going from y to each one of them. And well, for z and w, there are no critical points of smaller index, so the differential is just going to be 0. And so the non-easy facts are that this map is indeed a differential, so it squares to 0. And therefore you can define the chain complex, and the homology of this chain complex is a topological invariant of the manifold. It's independent of F, and it's actually isomorphic to the singular homology of the manifold.
Is there a reason why we always work in C2? Or is it just that it doesn't?
To avoid saying orientations of.
It just saves. It just saves keeping track of orientation.
Yeah.
And you don't get anything more if you generally, if you do keep track of orientation. Is that right?
So in my case, for the applications I have in mind, no.
No, generally, of course, you might
Generally,
get
of
more,
course.
but
Yeah.
but you don't want to spend the whole day to talk about orientations.
Okay, that's fine. I've just always wondered.
No.
It's a philosophical
Yeah.
question.
No, it's just
It's easier. Otherwise, I would have to say sign count, and why is this the minus of that? I don't want to get into it. Okay, so we have homology being the singular homology of the manifold, and then this answers our question basically. It tells us that the number of critical points any Morse function has is at least the dimension, the singular homology of the manifold, or the sum of Betti numbers. Now, having this construction of Morse homology, we can define numerical invariants of the function f, which basically measure the height in which classes in Morse homology appear. So these are called spectral invariants, spectral numbers sometimes. So the definition is the following. You take a class, alpha, in the singular homology of M. You can identify it with the class in the Morse homology of F, because they are isomorphic. And then you define the spectral invariant of F with respect to alpha to be the smallest value of a representative of the class alpha in the Morse chain complex. Okay, so let's go back to our example. And maybe make this sphere into a torus so that we have a little more homology classes. Right. So this is my function f. And now we have even more saddle points. So these are the critical points. And let's see what will be the spectral invariant of this function f with respect to the fundamental class. So the fundamental class lies in degree 2. We have only one critical point in this degree, so it must be represented by this one, uniquely represented by this one. And so the smallest value of f in which we see the fundamental class is the maximal value. Okay. Okay. Another one is, let's look at this non-contractible loop gamma. So you can show that this non-contractible loop gamma is uniquely represented by the saddle point, let's call it x. And so the first time it appears is when this x appears, so it's f at x. And a slightly less completely trivial example is the class of the point. So the point class is actually represented by both of these functions, these points, z and w. So each one of these minimum points represent the point class. And so the spectral invariance is going to be the smallest value among these. So this will be just the global minimum function f. Okay. And in general, it always holds that the spectral invariant of the fundamental class and the point class is the global maximum, the minimum of the function, just because how the Morse chain complex behaves. So this is what I wanted to say about Morse homology, and now I want to move on to talk about what we are studying in symplectic geometry. In symplectic geometry, we study symplectic manifolds. So these are even dimensional manifolds that represent the phase space of a mechanical system, right? So we have the same amount of directions for position and momentum, and these manifolds are endowed with a closed, non-degenerate differential 2 form that is basically used in order to write Hamilton's equations of motion in a coordinate-free way. So, or in other words, you can think of this 2 form omega as encoding the position momentum pairing. So it will tell you each position direction, what is the corresponding momentum direction. Okay, so in such a manifold, we consider smooth functions. We allow them from n to r, but we allow them to be time dependent. So here I think of the S1 variable as the time. So these functions are called Hamiltonians. They represent the energy of mechanical systems. And if we solve Hamilton's equations of motion with respect to F, we get a flow on the manifold, which represents the physical flow. And this is called the Hamiltonian flow. Of F. So now we have flow, interesting one. And one question we can ask, a very natural question, is does it have a periodic orbit and how many? And this question is addressed by Arnold's conjecture. Which states that the number of one periodic orbits Hamiltonian flow is at least sum of Betty numbers. So now, what we would like to do in order to get a lower bound for the number of one periodic orbits is basically mimic the construction in Morse homology, and for that we need to find a functional, more likely a functional, whose critical points are in correspondence with the one periodic orbits of the Hamiltonian flow. So this is basically what is done by Floer homology. So the functional we need to consider is called the action functional. It's denoted by A sub f. It's defined on the space of contractible loops in M. So this is the space of contractible loops, and it's defined by, so if we have a loop, its action is going to be defined by integrating the Hamiltonian along the loop and subtracting the area kept by the loop. So AF of gamma is the integral of F over gamma minus the omega area of a disk D capping gamma. So now you should object and say, well, this thing depends on the disk you chose. So this is true. This depends on the disk D unless pi 2 of M is 0. So if the second homotopy group vanishes, that means that every sphere is contractible to a point, or in other words, if you have two disks sharing the same boundary, then they are homotopic to each other. And so if you evaluate a closed form on them, you get the same answer. Okay. So this is, you already see where this pi 2 of M is not being 0 or non-zero enters the story. And tell me if the red is visible, but if pi 2 of M is not 0, and you need to consider some covering space of this space, basically accounting for disks, and then the action functional will depend on the disk as well. Can you see the red?
I can see it. I already understand.
Okay. All right. So now we have this functional and as I said, the reason we look at it is that its critical points correspondence with the one periodic orbits of the Hamiltonian flow. And now, assuming that many things behave like we want them to behave, then we can sort of try to mimic this construction of more somology. So you want to construct a chain complex called the Floer chain complex associated to F. This would be generated as a vector space. Again, we work with C2 by the critical points of this action functional. And then the differential, so maybe let me draw a picture. So we have, right, so suppose this is our manifold M. And here we have the loop space of M. So on the loop space, we have this actional function loop. And its critical points correspond to one periodic orbits of the Hamiltonian flow here. And then we're going to define the differential by counting negative gradient flow lines of the action function. And for that, we need to choose a metric on the loop space, but I'm not going into that story. So the picture is, we have the action functional, we want to count negative gradient flow lines here. So these are lines in the loop space, so they are paths of loops. And so in the base manifold, they look like cylinders connecting to periodic orbits. Right. So these are actually maps from the cylinder to M. And the fact that them being negative gradient flow lines amounts to them being solutions of a Cauchy-Riemann type partial differential equations called Floer equation. And I'm gonna refer to these negative flow lines as Floer trajectories. So then the even harder facts are that this differential also squares to 0. So under some assumptions that I'm not really specifying. Differential squares to 0, so it is a differential basically. And so you can look at the homology of this Floer chain complex. And the claim is that it is independent of F, the topological invariant of the manifold, and it's isomorphic to the singular homology of the manifold if to a value 0, and to something slightly more complicated called the quantum homology of M if not. Okay, but you should think of this quantum homology as singular homology tensor with some rings. So it's something that contains the singular homology. And so the corollary is that when this works out, you get Arnold's conjunction. Now, as in Morse homology, we can extract these spectral invariants, these numerical invariants from this construction, and now they are going to be dynamical invariants. So they're going to see the flow in some sense. So spectral invariants well, basically, for any class alpha, the spectral invariant of F with respect to alpha is going to be the smallest value, but now the value is measured by the action functional. So it's the smallest action of a representative of the class alpha in the Floer chain complex. And these spectral invariants are in general much more complicated than the ones coming out of Morse homology. So for example, the spectral invariants of the fundamental and point class are in general could be very difficult to compute. So they're not the maximum of the function in the general case. Okay. These spectral invariants have a lot of applications to study dynamical properties of the flows. So a very partial and biased list, the K is, well, you can use these spectral invariants to detect periodic points of the flow. So basically points that are mapped back to themselves after integer iteration. You can use them to study Poisson brackets. Basically to measure how non-commutative two Hamiltonian flows are. Yes, there are, so maybe I should say here, a lot of other applications that sort of are not as relevant to the story here, so I'm not writing it down. Okay, but some of the applications, specifically these two, consider spectral invariants of Hamiltonians or Hamiltonian flows that are supported on a subset of the manifold. So this sort of brings us to the second half of the talk, which is Hamiltonians on subsets. Okay, so the picture is here. We have our closed manifold, and we have a subset V, and then we have a Hamiltonian, which is supported on this set, or maybe this set is disconnected. So maybe we have another connected component here, and then our Hamiltonian actually splits into F1 and F2. This is V1 and V2, so on. Okay, so studying spectral invariants of such Hamiltonians can be used to both detecting periodic points of such Hamiltonians and to study rigidity of Poisson brackets. And so far, most of the work studying spectral invariants of such Hamiltonians did it in an indirect way. So basically what they did is they looked at the functional sending F to its spectral invariant, say with respect to the fundamental class, for example. So this functional has a bunch of nice properties. And then just by analyzing these properties and not even knowing where it came from, you can derive information on how it behaves in the case where your Hamiltonian is supported on subsets. The downside of this approach is that it kind of seems like the results you can get in this way are not very sharp. So there are a bunch of assumptions that seem to be coming from the tools you're using. So a natural idea would be to try and analyze the chain complex directly of non-degenerate perturbations of such Hamiltonian. Right, so the picture is you have a flow supported on some subset, and you want to perturb it to get something that is non-degenerate, and afterwards you want to analyze the Floer chain complex and hopefully separate in some sense what's happening in the support and outside. Right? Now, our chain complex was, well, it involved periodic orbits and these cylinders that connect them. So the periodic orbits are not they split nicely, right? So after a perturbation, you're going to have some non-trivial periodic orbits here and some critical points outside. So the more complicated part is these cylinders. So a priori, there's no reason why you wouldn't have cylinders connecting periodic orbits in different connected components of the support, or a periodic orbit inside with a constant orbit outside. Okay, so if we want to somehow split the chain complex into stuff happening inside and outside, we need to somehow rule out a bunch of cylinders going in and out of the domain. Okay. So this is basically what we want to do. And now a general rule of life is that if you want to prove something in Floer homology, you should make sure that you know how to do it in Morse homology, because Floer homology contains Morse homology as a special case. So let's go back to Morse homology, see what the analogous problem is and how to solve it. So the analogy in Morse homology is we have a Riemannian manifold, and then we have a subset V of this Riemannian manifold, and we have a smooth function supported in this subset, and we want to perturb it into a Morse function in such a way that the Morse chain complex will split into stuff happening inside and outside. And it's not difficult to arrange for the critical points to lie either inside or outside. So the main question is about negative gradient flow lines. So we want to prevent negative gradient flow lines from going in and out of the support. And so the natural thing to try and do is to create a small bump around the neighborhood of the boundary. So something like this. Okay, so we created a bump. So what's happening now? What did we achieve by creating this bump? So now, flow lines, called the mu of minus gradient. Let's call this perturbation f epsilon. So flow lines of minus gradient f epsilon satisfy the following. So if they start
is the bump inside the support?
Yes, it doesn't really matter, but yes. So I assume that my function is compactly supported in this open domain, and then I have just, yes, like the bump is in the domain outside of the actual support. Okay.
But then there will be some critical points on the bumps which are actually flowing outside, right?
Yes, I will get to it in a moment, but exactly. Okay, so we have, if our flow line starts inside, but away from the neighborhood of the boundary, so not on the bump, then, well, the picture is, if we start here, then we go down, and then we cannot climb on the bump. So we're stuck in the same region. So then this U is going to be contained in V minus the neighborhood of this boundary in which we created the bump. If we end in the domain V, so if we end up here, then we could either start from an interior critical point, or we could start from a critical point on the bump, but we cannot start outside because we cannot climb on the bump. So U will be contained in V. But as Camilo pointed out, if U starts on the bump, then it can flow both in and out. So the picture is we start here, we can flow out, we can flow in. Okay, but this is actually expected. So you cannot hope to have the differential completely splitting into stuff happening inside and stuff happening outside. Otherwise, the homology would split into stuff happening inside and stuff happening outside. And I told you that we're supposed to end up with the homology of the manifold, and we know by Meyerbeer that gluing homologies of such pieces is not as simple as a direct sum. Okay, but these are some restrictions, and we know that the differential in the Morse homology counts these negative gradient flow lines, and we hope that we can get somehow some information. Okay, so we can, but I will say in a moment what is the information you get on the differential. After I will tell you that it turns out that if you assume that pi 2 is 0 and the domain V is nice enough, then you can adapt this picture to Floer homology. So basically, back Floer homology, then maybe I'll write it here. So the claim is, and this was obtained jointly with Yaniv Ganor. So the assumptions are, assume that this second homotopy group finishes. Assume that the domain V is nice enough. So for example, it's enough to assume that it's disjoint union could be also one connected component, but in the more general case, disjoint union of symplectic embeddings of star-shaped domains in R2N into M. And for the symplectic people in the audience, I will say that it's enough to assume that the boundary of V is contact and incompressible. Okay. And well, naturally, we're going to have our Hamiltonian supported. So,
What incompressible?
okay, sorry. So incompressible means that the map induced by the inclusion on I1 is injective, or in a less algebraic language, if you have a loop in the boundary and it's contractible in the manifold, it has to be contractible within the boundary.
So it's the usual topological.
Yeah, usual topological incompressibility. And this seems like a very weird condition, but it's absolutely necessary. So, okay, so if we have these assumptions, then there exists a perturbation silent F and a choice of metric complex structure, if you know what it means, on so metric on the loop space of, or a almost complex structure on the manifold, such that every negative gradient flow line of the action function with respect to silence satisfies these restrictions. So let's call it star. Put a star here. And I can say that actually this theorem also holds for homotopy of Hamiltonians, and then you can deduce corollaries for trajectories that are participating not in the differential, but in chain maps between complexes of different Hamiltonians. Okay, this is like a not very important. So having these restrictions, what can we know about the differential? So as in the Morse case, it's not going to split into a direct sum of inside and outside. But if you look at the correct vector space decomposition of the chain complex, the differential is going to take a triangular block form. So like next best thing. So the corollary. So let me illustrate this decomposition on the picture. So suppose here's the domain V, here's the boundary of V. Here, the neighborhood of the boundary in which we created this bump. And this is where the support of the original Hamiltonian lied. So here's the non-trivial dynamics. Here we have some critical points on the bump and some critical points outside. So we're going to call this region domain number 1. This will be number 2, and this will be number 3. So we split the complex into a subspace generated by the non-constant periodic orbits inside, plus critical points outside, plus critical points on the bump. And then the differential takes the following form. So here you have the restriction of the differential into V minus the neighborhood of the boundary. Then you have 0, differential restricted to V, something, something, differential restricted to V, 0, 0, 0. And when I say differential restricted, I mean that this map counts only trajectories that are contained in V. So this map doesn't see and doesn't care what happens outside of V. And in particular, what happened is that the first component here is a subcomplex. So Ci and differential restricted to this region. This is a subcomplex. And its homology, what is it going to be? Well, the homology of V. So in this sense, we sort of decomposed the Floer chain complex and sort of managed to sort of separate the important part of, containing the non-trivial dynamics. Okay.
How is the second thing on the top row 0?
Again,
Like coordinate 1, 2.
this?
Yeah.
Why is this one 0?
Yeah.
So let's see. So we have here Ci. So this one will go from 2, which is outside, to 1.
Oh, okay.
So it's,
So C2 is also a subcomplex, yeah?
yes, but it's not a very
Not
interesting.
very interesting one, but it is.
Yes, but, okay. It is a subcomplex, but we don't guarantee. I mean, I think it should be possible to do, but we don't guarantee that that the map restricted to it will not pass through this domain. So that it doesn't count like trajectories going through the interior of it. So we don't rule out these things. I think they're critical points, but you know what I mean. So it's like a
Because it's
less,
contact type with respect to 3 or 1.
yeah, with respect to this, yeah. Mhm. Yeah.
Well, you
I mean-
kind of do because outside you only have constant. I mean.
Yes,
Okay,
but-
you assume pi2 is equal to 0, right?
Mhm.
So they should only be gradient trajectory treated as that.
You should, well, anything that is contained here. So the Hamiltonian is small here.
Yes. But no.
So here it should be gradient trajectories. But if you have something that visits the area where the Hamiltonian is not small, then the argument is not working for that, right?
But maybe one could say if the
Because you need
star and the
globally
energy
Hamiltonian.
is small, then it can't
Yeah,
really
the
get there.
difference is small.
So I said I expect this.
See, I don't think they go in that side. Okay.
Yeah,
So
so
you could say, let's
I think-
assume, and then you make the Hamiltonian
So
small.
if you're willing to say like a more spot thing, if you're willing to say,
Yes.
like I believe convergence to cascades, then you can arrange the difference here to be smaller than some width here. And then,
And so that, sorry,
So-
maybe it's a silly question. So that sort of red sausage would be a solution of
It's actually a
of your
bundle.
Floer,
Floor.
right?
Yeah.
Which is elliptic. So if it's going to be a flow line for a certain time, I mean, wouldn't you have some
Yeah, if the
unidirectional
Hamiltonian is
argument?
small, then it should sort of collapse on a flow line, which it wouldn't
But-
go there.
this argument uses that the Hamiltonian is small on the whole
Yes.
trajectory. And if your sausage visited the area where the Hamiltonian is not small,
Well, I'm somewhat mystified by the fact that there could be a solution of an elliptic PD, which is kind of degenerate,
No, it's not.
right? And then it becomes non-degenerate.
No, it's not.
Yeah,
No,
no.
it doesn't start as a flow line. it
Yeah,
comes-
this is the, look at the picture.
By unit continuation.
Like what you would expect is some-
Yes, that's what I was thinking. You know, by unique continuation, it cannot be a flow line at the
But
beginning.
you don't know
and
that
then
it started.
It's near a flow line.
it's near a flow line.
Yeah, it's near.
Okay, so it's really a sausage. It's not like, you know,
It's
it's
really
not like just
Yeah, sure.
just not just like, you know, just the
It's
string of the
your
sausage.
interaction
is
Okay,
different.
okay.
Okay,
But otherwise, as an elliptic PD, it's an honest elliptic PD, which has the unique continuation property.
yeah.
Okay,
So the only thing I think what Kyle said is if you take the perturbation very small from the flow line, say, then it would need some energy to get there,
Yes.
and therefore it won't get there, and then it's a flow line.
Yes,
yes, okay, I understand. I mean, like it's the equivalent to say that, okay, so if you're very, 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 very close to be degenerate, you will actually need quite a lot of energy to like open it up.
Yeah.
Okay.
Yeah. So as I said, this is like probably true, but I haven't written it down, so I'm not guaranteeing. Okay, but in any case, somewhere of this part, the other part is less, I would say, interesting. All the critical points there, and you're just gonna get like more somology. Okay, so having this splitting or decomposition, you can derive applications to spectral invariants and to other quantitative measurements from Floer homology, but I will talk only about spectral invariants. So
May I ask you another silly question?
sure.
So V is the joint union of embeddings of star-shaped domains.
Yes.
So the homology is really on that.
Yes.
This is something.
Yes, but there's like a bracket underneath that you can actually do more general domains.
She didn't want to explain.
That bracket, okay, because it's incompressible. Okay. Now I got it. Yeah, okay. So that one, of course, is topologically complete. Okay.
Yeah.
Yeah, I got it.
Okay, so using this information about the Floer chain complex, you can know a bunch of stuff on spectral invariants. So the first thing you can know is basically that the spectral invariants of Hamiltonians supported on such domains, on such manifolds, are independent of the ambient manifold. So they don't see the topology of M outside of the support. And this is not trivial because, I mean, they are defined with respect to a homology that results in the homology of the whole manifold, right? So let me draw this on a picture instead of making a formal claim. So suppose we have V, which you can think of as a star-shaped domain in R2N, but could be something else. And suppose that it symplectically embeds into two different closed manifolds. Something like this. So here we have the image. of V. And then if you have a Hamiltonian supported on this domain, you can push it to Hamiltonians on the closed manifolds simply by using the embeddings and extending the zero. Now you have two Hamiltonians on closed manifolds. You can compute their spectral invariants, say with respect to the fundamental class. Same here. And the claim is that these two coincide. Okay, and this is true for a bunch of other classes, basically any class that is in the image of the map induced on homology by the inclusion or the embedding. Okay. Right, so this is one application, and another application, sorry.
You're taking the fundamental class of M,
Oh, sorry.
which is
No,
which is
no,
not quite in the
N. I'm sorry.
no, but
No, okay, so in addition, you can show this statement directly, and you can show that also for any, okay. To convince you that this actually follows from what I said is that you can use Poincare duality, and then the point class lies in the image. But you can also prove this directly.
yeah, no, I believe that.
But in general, if you want to
For other
extend it,
classes, you really want them to be in the image.
oh, for other
Other
classes,
classes,
I need it to be in the image or like in some sense completely orthogonal to step in the image. So anything that's like a mix-up, you can, I don't guarantee any. Yeah, you could have like different results. Okay. The second application concerns something more similar to this picture. So basically, there are a bunch of works studying spectral invariants of Hamiltonians supported on several connected components, so disjointly supported Hamiltonians. And people are interested in upper bounds of the spectral invariant of the sum, so the total Hamiltonian. And there are several reasons to be interested in that. One of them is this Poisson bracket application that I mentioned. Another reason is that in some specific cases, you can somehow gain information on global Hamiltonians by studying the pieces and so on. Okay, so a very nice result in this area was due to Migliele, Roy, and Fadini. So they proved the theorem, which is called the Max formula for spectral invariance. So the assumptions are the same as in this theorem. So phi2 is 0, and VI, these are the connected components of the V. So they are embeddings of square-shaped domains. And Fi are supported in VI. And then the claim is that the spectral invariant of the sum is exactly the maximum with respect to the fundamental class, sorry, is exactly the maximum over the invariant of the sum. Okay. So in terms of getting upper bounds for the spectral invariant of the sum of such Hamiltonians, this is very nice because it's sharp, it's a formula. But then if you want to extend it to other classes, then it's not going to be true. And the reason is basically, so this is not true for other classes, general alpha, and the reason is Poincare duality. So basically, the class of a point is going to satisfy a min formula. So here you would have a minimum instead of maximum. But what does hold for a general homology class is an inequality. So this is another application of this sort of splitting for any homology class alpha. Under these assumptions, yeah, the spectral invariant of the sum is smaller or equal than the maximum. Right, and I want to mention that this theorem is, well, the analog in Morse homology is completely trivial, right? Because in Morse homology, the spectral invariants with respect to the fundamental class are always the maximum of the function. And then this statement is just saying the maximum of the sum of disjointly supported functions is just the maximum of the maximum, right? But for a general homology class, it's not completely immediate, even in Morse homology. It's a fun exercise. It's not very difficult, but you need to say something. Right. How am I doing with respect to time?
8 minutes.
Okay, great. So basically everything I said so far is under the assumption that pi2 is 0. So what happens if pi2 is not 0? Then basically everything fails. I mean, by fails, I don't mean that we don't know how to prove it. I mean that it's wrong. So you cannot hope for such a splitting. These applications are not true. So for example, here, not only that spectral invariants can see the topology outside of the support, they can see the omega area of the complement. So for example, if you embed a disk into two different spheres, one of large area and one of small area. Picture is small area part, and then you are embedded it to a sphere with a large area, then you're not going to have the same spectral invariance here and there. I mean, for general Hamiltonians. Okay, so these are very sensitive to the symplectic geometry support. And also here in the theorem by Omidyela, Lorenzi, Fedini, they showed that this formula is not true if on the sphere, basically on the two sphere. So they constructed, maybe I'll do it here. So they constructed an example. Maybe I'll move on. Specific Hamiltonians supported on the upper and lower hemispheres, for which the spectral invariant of the sum, with respect to the fundamental class, is strictly smaller than the maximum. Okay, so this kind of seems like there's not much we can hope to say about splitting in this case. But I mean, having this inequality, a natural question, which is also motivated by some of the applications, is maybe an inequality holds in a more general setting. So the question is, when is it true that the spectral invariant of a sum of disjointly supported Hamiltonians with respect to the fundamental class, say, is smaller or equal than the maximum? Okay. And it turns out that this question can be answered to the positive in a bunch of settings. So for example, if your Hamiltonians are supported in small, far enough balls. I mean, you can do more general than that, but I don't want to start defining a lot of things. So let me just give an example statement. So assume that the areas of spheres, so the image of their omega of pi2 of m lies in some lattice. Such manifolds are called rational. And assume that the domains VI are, so VI is embedding of a ball of radius Ri. And I want to say that these VIs are far from each other, and the way I will say that they're far is basically by saying that there's a bigger ball containing it, and these bigger balls are disjoint. So the embedding extends to a ball of twice the size, and extensions are disjoint. So the picture is you have balls, And then you demand that you have a bigger ball surrounding these, and the bigger balls are disjoint. And take Fi to be supported in Vi, and we're going to assume that either the spectral invariants of these are small or the balls are small. So either spectral invariant Fi is smaller than kappa, or size of the ball is not greater than kappa. And I should say that it is known that the latter implies the first. Okay, then the max inequality holds. So then let me call this max inequality. This max inequality. So I should say that for the symplectic people, you don't need to consider balls. If you have a contact boundary, there is a way to make precise of the size of the neck, right, by the time of the Liouville flow. And then, so basically the size of your symplectization neighborhood in the manifold should be disjoint, and then the size of this symplectization neighborhood also comes into how small the spectral invariant needs to be for this to hold. Okay. But these statements, so basically all of the settings in which this max inequality is established, these theorems are proved also in a rather non-direct way. And so a work in progress is to provide a more direct proof that will hopefully enable to remove some of the assumptions. So in progress. More direct analysis.
So if you would know that holomorphic spheres would, even if this is true, would have a bigger area than kappa, then you could maybe improve this result.
So kappa is exactly like the smallest area of.
Right, but
if I know that specifically for holomorphic.
Yeah, because I mean, this is a worst case scenario.
Yeah.
If you would know by some other reason that holomorphic spheres are bigger than
it would help. So it wouldn't help for the indirect proof because it doesn't see what really it's going on. And that's why I'm sort of, so let me say maybe a word about how I hope to get rid of the size of this kappa, which doesn't seem natural here. So the point is that this thing actually comes from the fact that you don't know, if you don't work, you don't know what the differential is doing outside. And outside, your generators of the complex are critical points and spheres. So cappings of critical points, they are just spheres. And then you don't know what the differential is doing. And if you work and do analysis, the hope is to say that differential acts very simply, and then these shouldn't mess up the computation. So Floer chain complex in this way, yes. And let me just finish with an open question. So I don't know of any example where this max inequality doesn't hold. So are there F1 and F2 disjointly supported on a closed symplectic manifold M such that spectral invariant of their sum with respect to the fundamental class is strictly greater than the maximum.
You have some intuition what you would most likely expect here?
No, but I mean, I would only try to answer this question to the negative because proving that this always happens is, I think, would be difficult. And I only tried so far things that are rather simple because, I mean, computing spectral invariants in general is, if you want to know the correct answer or not. So the first thing you can try to do is look at some, so there is like a homogenized version of these spectral invariants, right? Like basically if you take a limit over of C of K F divided by K, and then people know a lot of things about these things. So for example, you could replace the work here that too many other ones Affiliation did to show that you don't have equality in general just by using these things, and a work by Polterovich and Entov saying that the equator is super heavy, they call it. So basically, it is known that on some sets, spectral invariants are unbounded from below and above. And you can try to use these facts to for example, you can use these facts to show this counterexample, and you can replace this counterexample, not exactly this one, but a similar one. But you cannot, I didn't manage to do this just by such considerations. And also I tried to analyze like radial Hamiltonians on surfaces. Didn't get anywhere yet.
Okay. So we were already at the stage of questions.
So this last theorem that you stated, does it follow from estimating the area of holomorphic or of Floer cylinders here?
This one?
Yeah.
No, it's completely indirect in the sense that it doesn't open the black box of the chain complex.
Can you briefly say how you do that?
Okay. Yes, so it's a modification of, so you know the old paper by Ciccadini called Spectral Killers. So basically the idea there was, so maybe I'll erase this. So he had a very, very nice trick, which was like, if I have a Hamiltonian supported on some subset, I can add a function, which is called the spectral killer, which the function I'm going to draw in another color. So the function we're adding is basically a pit-shaped function, okay? And then if I manage to show that the sum of these two have zero spectral invariant, then I bounded the spectral invariant of this by this. Okay, so I modified this construction so that the spectral killer sort of fits the Hamiltonian and not the set. And so the depth here is minus C of F. And so you don't simply add it, you add it via deformation. So you look at a deformation going from a continuous deformation going from F to this A, let's call it. And you follow the action spectrum. And you analyze the action spectrum and you sort of try to see, and you use the fact that here the non-constant periodic orbits of K are in correspondence with the red dynamics on the boundary. And then you can know somehow, in some cases, you can know that you landed up at zero. Right? And the inequality will be obtained by, well, if you do it in a bunch of places in the manifold, then the spectral invariant of the total thing is smaller than the C0 norm of this K. But the C0 norm is exactly the spectral invariant.
More questions?
So now that you've shown in that application number 1, that those two numbers are the same, does it make sense to try to embed your like domain into many things to try and compute things? Does
Yes.
that give you any?
Yes, so in particular, when your domain that you started with, so first there is like, you can cook up a capacity out of these spectral invariants, basically by taking like, I mean, it's an approximation what I'm saying, but taking the largest spectral invariant of Hamiltonian supported in the set. So this will be a capacity, and actually the finiteness of this capacity implies existence of periodic points, of infinitely many periodic points. And you can show that this capacity is bounded using this just by saying, okay, maybe I don't know that my set is displaceable in here, in one of the manifolds, but I can shove it into maybe a very big torus. And in this torus, it will be displaceable, and then it's finite. So yes, it's used to estimate these things.
Okay, if there are no more questions, I guess we can enjoy our tea and thank Shira